Hey guys, how's it going? In this video we're going to go over section 1, i.e. the multiple choice questions from the 2024 SQA National 5 Physics exam paper. Now there are 25 questions in this section and I recommend that you try them yourself before looking at these solutions. So let's get into it. Question 1 says, which row in the table classifies speed, weight and energy correctly? And our options here are scalar and vector. Well, remember a scalar quantity has a magnitude or size only, whereas a vector quantity has both a magnitude or size and a direction. So for these we just need to think about where direction is important. So firstly we have speed, which is a scalar because we don't care about direction when we're talking about speeds. We then have weight, which is a vector because remember weight is a type of force and force is a vector. So we do care about directions when we're talking about weight and force. And lastly we have energy, which is a scalar, and that's because we don't talk about directions when we're defining energies. So that means we have scalar, vector, scalar, which gives us the answer E. Question 2 says a student uses the apparatus shown to determine the average speed and instantaneous speed of a trolley as it travels down a slope. The trolley is released to X and travels down the slope, so that's point X at the start there. The distance between X and the light gate at Y is D, and you can see that labelled on the diagram there. The time taken for the trolley to reach the light gate is T1. The length of the card on the trolley is L, and that's labelled on the card there. And lastly it says the time taken for the card to pass through the light gate is T2. And you'll see in the diagram as well we've got a stopwatch to measure T1 and the electronic timer measures T2. It then says which row in the table shows the measurements required to determine the average speed of the trolley between X and Y and the instantaneous speed of the trolley at Y. Well, here we need to think about our definitions of average speed and instantaneous speed. Well, we can say that average speed involves the total distance between X and Y, which is D in this case, and the time taken to travel that distance, which is the time T1 measured by the stopwatch. And we also have the instantaneous speed involves the length of the card, which is L in this case, and the time taken for the card to pass through the light gate, which is T2. And T2 is measured by the electronic timer. So that means for the first column, measurements for average speed between X and Y, we would want to use the distance D and the time T1. So it's either going to be B or E here. And then for the second column, measurements for instantaneous speed at Y, we've said that we need the length of the card L and the time from the electronic timer T2. And that means E is not going to be our answer here because that says L and T1. And that means our final answer here with D and T1 for average speed and L and T2 for instantaneous speed is the option B. Question 3 says a rocket is taking off from the surface of the Earth. The rocket engines exert a force on the exhaust gases. Which of the following is the reaction to this force? Well, remember for Newton's third law statements or Newton pairs like this, we just need to swap the order of some of the words. So instead of the rocket engines exerting a force on the exhaust gases, if we swap rocket engines round for exhaust gases, then we've got the exhaust gases exerting a force on the rocket engines. And that is given by the last statement here, the force of the exhaust gases on the rocket engines. So that means my answer here is E. Question 4 says a motor raises a mass of 2,400 kilograms vertically through a height of 5.0 meters in 2 minutes. The minimum power rating of the motor to raise the mass is... Well, notice how we're asked to calculate power here, but we're given things like mass and height, which we need to use first of all to find an energy. So let's use our equation for gravitational potential energy, EP equals mgh, which depends on mass and height, which we have, and gravitational field strength. So substituting in our numbers, we have 2,400 for the mass, times 9.8 newtons per kilogram on Earth, times 5.0 meters for the height, and putting that into your calculator should give you an answer of 117,600 joules. And notice how I'm not rounding at this stage. And now that we have an energy, we can think about the power equation that relies on energy and time because we're given time in the question as well. And remember that equation is P equals E over T, or in this case I'm writing EP because that's gravitational potential energy. So substituting in our numbers, we have 117,600 divided by 2 times 60, where we're converting the 2 minutes into seconds, and then putting that into your calculator should give you an answer of 980 watts, which is the answer B. Question 5 says a satellite is in circular orbit around the planet. A group of students make the following statements about the satellite in orbit. Statement 1 says the horizontal speed of the satellite is constant. Statement 2 says the satellite does not move. And lastly, statement 3 says while orbiting the planet the satellite is weightless. Which of these statements is or are correct? Well, firstly, let's just remind ourselves about satellites. So remember, a satellite is a special type of projectile that orbits a planet. It has a constant horizontal speed and constant vertical acceleration, giving rise to the circular path. And we can say a satellite is in a constant state of free fall around the planet. So if we look at statement 1 first of all, the horizontal speed of the satellite is constant. Well, we've just said all satellites have a constant horizontal speed, so that must be true. For statement 2 saying the satellite does not move, well, we've just said that a satellite is in orbit around the planet and it's in a constant state of free fall, so it must be moving. So that means that second statement is false. And lastly, statement 3, while orbiting the planet, the satellite is weightless. Well, that's not entirely true. There is something called apparent weightlessness, where a satellite or astronauts inside a satellite or spacecraft will feel that they are weightless, even though they're in a constant state of free fall around the planet. So they're constantly accelerating towards the surface of the planet. And they cannot be weightless because there is gravity in space. It's just weaker than in other places. So that means we have the first statement only is correct, which gives us the answer A here. Question 6 says a pulse of light from a laser is transmitted from the Earth to the Moon. The light reflects from a mirror on the Moon and is detected back on Earth 2.6 seconds after being transmitted. The distance from the Earth to the Moon is? Well, firstly we need to find the distance travelled by the light, which we can find using speed distance time. So we've got distance equals speed times time, substituting in the numbers gives 3 times 10 to the 8 for the speed of light, times 2.6 seconds, which was the time value we're given, and putting that into your calculator should give you an answer of 7.8 times 10 to the 8 metres. And remember, this is not our final answer because we want the distance from the Earth to the Moon, but we're told that the light reflects from a mirror on the Moon. So that means the light's travelling from the Earth to the Moon and then back again to the Earth. So what we need to do to find the distance between the Earth and the Moon is half our answer there. So we need to do 7.8 times 10 to the 8 divided by 2, and putting that into your calculator should give you an answer of 3.9 times 10 to the 8 metres, which you'll see is option D. Question 7 says the table shows the altitude and period of 4 satellites. So we've got the International Space Station, APRI's Sat-3, Intelsat 18 and Hubble Space Telescope. And notice how the altitude's in kilometres and the period's in minutes. And if you've forgotten what altitude and period are, remember that altitude is the height above the Earth's surface in this context, and the period is the time taken for one full orbit of the Earth. It then says the period of the APRI's Sat-3 satellite is... So what we need to do here is look at the patterns of the numbers. So we've got 686 kilometres for the satellite that we're interested in, and we need to predict its period. And remember, there's only going to be one right answer here. So we can say that since 686 kilometres lies between 537 kilometres, which is this one, and 35,800 kilometres, which is our next highest one, the period must lie between the periods of these satellites. That is, the period must lie between 95 minutes and 1,440 minutes. And if we look at our options, the only one between 95 and 1,440 is C, 98 minutes. Question 8 says a student makes the following statements about the universe. Statement 1 says 1 light year is the time taken for light to travel from the Sun to the Earth. Statement 2 says the approximate age of the universe is 13.8 billion years. And statement 3 says the Big Bang Theory describes the origin of the universe. Which of these statements is or are correct? Well, let's go through each one in turn and decide whether they're true or false. So for that first statement, 1 light year is the time taken for light to travel from the Sun to the Earth. Remember, the light year is not a time, it's a distance. And our definition is this: 1 light year is the distance travelled by light in 1 year. So that means that first statement is false. For statement 2, the approximate age of the universe is 13.8 billion years. Well, that is true, it's almost 14 billion years old. And lastly, statement 3, the Big Bang Theory describes the origin of the universe. That is also true, it's one of several theories that exist. So that means we have statements 2 and 3 being correct here, which gives us the answer D. Question 9 says an electric field exists around 2 point charges Q and R. The diagram shows the path taken by a charged particle as it travels through the field. The motion of the particle is as shown. So you can see the particle moves sort of straight, and then when it gets near point charge Q it bends towards charge Q, and then when it gets towards point charge R it bends towards it, and then it travels straight again. It then says which row in the table identifies the charge on the particle, the charge on Q and the charge on R. Well, since the charged particle bends towards Q and bends towards R, that means it's attracted to both Q and R, which means it must be oppositely charged to Q and R, and that Q and R must have the same charge. And that means we can eliminate some options here, because if Q and R have the same charge due to causing the same attracting effect on the charged particle, then they can either both be negative or both positive. So our answer is either going to be A or E. It cannot be B, C or D because those are showing opposite charges for Q and R. And then you'll notice how option A has the charge on the particle being positive, which is opposite to the charge in Q and R, whereas option E has the charge being positive, which is the same as charges Q and R. But remember, positive and negative charges attract, so we must have that the charge on the particle is opposite to that on Q and R. So we cannot have answer E, which means we're left with option A here, so A is our answer. Question 10 says a toaster is connected to a 230 volt main supply and switched on. The heating element in the toaster has a power rating of 1.2 kilowatts. A student makes the following statements about the toaster. So statement 1 says the heating element transfers 12,000 joules of electrical energy each second. Statement 2 says the plug of the toaster should be fitted with a fuse rated at 13 amps. And statement 3 says the charge passing through the heating element each second is 230 coulombs. Which of these statements is or are correct? So looking at that first statement, the heating element transfers 12,000 joules of electrical energy each second. That is referring to the definition of electrical power, which remember is the electrical energy transferred each second. So if we've got a power rating of 1.2 kilowatts, remember that's the same as 1.2 times 10 to the 3 watts or 1,200 watts, which would mean our energy transferred is 1,200 joules of electrical energy each second, not 12,000 joules. So that first statement is wrong. Statement 2, the plug of the toaster should be fitted with a fuse rated at 13 amps. Well, remember we can say that for appliances over 720 watts, this threshold value, we can use a 13 amp fuse, whereas anything below 720 watts we can use a 3 amp fuse for. So that means statement 2 is correct. And lastly, statement 3, the charge passing through the heating element each second is 230 coulombs. Well, here we need to remember that charge passing each second is the same as a current. In other words, from the equation Q equals IT, if you rearrange for the current I, you get that I equals Q over T, i.e. current is the charge divided by time. So the charge passing each second is the current, so we want to calculate a current here. And remember we've got a power and a voltage to do that, so we can use the equation P equals IV. Substituting in the numbers, we have 1.2 times 10 to the 3 equals I times 230, and to find I you can do 1.2 times 10 to the 3 divided by 230 in your calculator to get an answer for I of 5.2 amps. And now that we have a current value, we can use the equation Q equals IT, where we're going to use 1 second for the time because we're asked about each second. So this equals 5.2 times 1, which gives 5.2 coulombs. So that means this final statement is false, which means that statement 2 is the only correct one, which gives us the answer B here. Question 11 says a circuit is set up as shown, and you can see it's a series circuit with 2 resistors and 2 voltmeters. And another way of thinking about this is that it's a potential divider circuit. And it then says the reading on voltmeter V1 is 3.6 volts, so that's up here, and the reading on voltmeter V2 is. So we need to calculate that voltage, which we can do using one of our potential divider equations. So because we don't know what the supply voltage is here, we're going to use the equation for potential dividers that doesn't have Vs in it. And just before we do that, let's label the resistors. So we're going to call this first one number 1, just like they've done in the question. So since that's voltmeter V1, we'll call that resistor R1, and since that's voltmeter V2, we'll call that resistor R2. So using our equation that doesn't have Vs in it, it's V1 over V2 equals R1 over R2, i.e. the ratio of voltages equals the ratio of resistances. And then substituting in our numbers, we have 3.6 divided by V2 equals 16 divided by 24. And then cross multiplying here, we can do 16 times V2 is equal to 3.6 times 24, which ends up giving us 16 V2 equals 86.4. And then to get V2 on its own, we can divide both sides by 16, so doing that in your calculator should give you an answer of V2 equals 5.4 volts, which is the answer E here. Question 12 says a circuit is set up as shown. So we've got a battery, we've then got an ammeter A1 next to an LDR, i.e. a light dependent resistor, and then we've got the single branch splitting into 2, so we've got ammeter A2 next to a resistor and ammeter A3 next to a resistor. And it says the resistance of the LDR increases as the light level decreases. The light level instant on the LDR decreases. So we're told that the light level is going down, so that means the resistance of the LDR must be going up. It then says which row in the table describes the effect of this change on the readings on the ammeters. Well, firstly remember that current splits up through each branch in a parallel circuit. So looking back at the diagram, we've got the current is the same at these points, but then when we get to here, the current will split up across these 2 resistors. So using our large rule here, light up resistance down for LDRs, we can use the opposite of that, which is light down resistance up. So if the light level on the LDR is going down, the resistance is going up. So if the resistance goes up, then the current must go down through the LDR. So if the current goes down here in this single path, then that means when the current splits up into the parallel part here, then the current is also going to be reduced in both of the branches. So that means that the current readings on ammeters A1, A2 and A3 are decreasing. So we're looking for decreases, decreases and decreases, which gives us the answer A here. Question 13 says 3 resistors are connected as shown. So we've got 12 ohm, 6 ohm and 4 ohm resistors in parallel, and it says the total resistance between X and Y is. Well, here we want to use our equation for resistors in parallel, so we have 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Substituting in our numbers gives 1 over 12 plus 1 over 6.0 plus 1 over 4.0, and then I'm going to use the lowest common denominator method here to simplify these fractions, but you can just simply plug this into your calculator if you prefer. So notice how the lowest common denominator here is going to be 12 because 4 and 6 both go into 12. So to get from 6 to 12 we need to multiply the top and bottom here by 2, and to get from 4 to 12 we need to multiply the top and bottom here by 3. So we have 1 over 12 plus 2 over 12 plus 3 over 12. And then we can simplify that into one fraction. So we have 6 divided by 12. But remember that's 1 over RT and we want RT. So here we need to flip both fractions round. So we get RT over 1, which is essentially just RT, is equal to 12 over 6. And that therefore gives us 2.0 ohms, which is the answer B here. Question 14 says a length of wire has a resistance of 8.0 ohms. The current in the wire is 1.5 amps. The power developed in the wire is. Well, we're asked to calculate power and we're given a current and resistance. So writing down our equation for power in terms of current and resistance, we have P equals I squared R. Substituting in the numbers gives 1.5 squared times 8.0, and putting that into your calculator should give you an answer of 18 watts, which is the answer C here. Question 15 says a student carries out an experiment to determine the specific heat capacity of copper. The setup used by the student is shown. So you can see we've got a 12 volt power supply with an immersion heater connected, which is inside the copper block. We've then got a thermometer inside the block as well, and we're told that the block has a mass of 1 kilogram, and we've also got a heatproof mat that the block's sitting on and a stop clock. It then says the student heats the copper block for 5 minutes. The temperature of the block increases by 14 degrees Celsius. The value of the specific heat capacity of copper determined by the student using this method is found to be inaccurate. Which of the following changes would improve the accuracy of this experiment? So we have heating the copper block for a longer time, placing insulation around the copper block, replacing the copper block with one of less mass, replacing the immersion heater with one of a higher power rating, or removing the heatproof mat. Well, if you think back to doing the specific heat capacity experiment, one of the main issues causing the accuracy of your final result for specific heat capacity to be different from what you expected is the loss of heat to the surroundings. So in order to try and prevent heat loss, one of the things you can do is place insulation around the copper block to try and reduce some of that heat being lost, and that means that more energy is going into heating the copper block rather than being lost to the surroundings. So you should end up with a more accurate value for specific heat capacity in the end. So that means our answer here is B. Question 16 says a solid substance is placed in an insulated container and heated. The graph shows how the temperature T of the substance varies with time T. So we've got this heating curve with temperature against time with the labelled parts P, Q, R, S, T and U. And it says to determine the specific latent heat of vaporization of the substance, a student would use the time from section PQ, QR, RS, ST or TU. Well, here we need to think about what's going on in the diagram. So if we start off at point P, we're told it's a solid substance to begin with. So as you heat up the solid substance, eventually you reach point Q where it starts to melt into a liquid. Between Q and R, the solid is going to be melting, i.e. it's undergoing fusion, and then when it reaches point R, it's going to have fully melted. So that means we've got a complete liquid at point R, and therefore we would use the specific latent heat of fusion between Q and R, not vaporization. And then if we think about increasing the temperature of our liquid further, then between R and S, we've got the increasing temperature of our liquid, and then at point S, that liquid is going to start evaporating. Between S and T, the liquid is going to be evaporating, and then finally at point T, that liquid is going to have fully evaporated into a gas. So since between S and T we have evaporation going on, then we can think about vaporization, i.e. it's between S and T that we would use the time for to determine the specific latent heat of vaporization. So that means our answer here is D. Question 17 says a syringe containing air is sealed at one end as shown. So there's the seal on the end of the syringe, and we've got a plunger which can move. It says the initial volume of the air in the syringe is 1.40 times 10 to the minus 6 meters cubed, and the pressure is 120 kilopascals. The plunger is pushed in, causing the volume to be reduced by 0.30 times 10 to the minus 6 meters cubed. The temperature of the air inside the syringe remains constant. The pressure of the air inside the syringe is now, so notice we're given those words in bold, reduced by, and since we've got volumes and pressures here and we're told that temperature remains constant, then we should be thinking about Boyle's law, which is the pressure and volume law. So remember our equation for the pressure volume law is P1V1 equals P2V2. Substituting in the numbers gives 120, where we're keeping the pressure in kilopascals, times 1.40 times 10 to the minus 6, that was the first volume, is equal to P2, the final volume, times 1.10 times 10 to the minus 6. And that's our second volume, where we were told that the volume had been reduced by this amount. So if we take 0.30 times 10 to the minus 6 away from 1.40 times 10 to the minus 6, then we get 1.10 times 10 to the minus 6. Don't be caught out there by substituting in 0.30 times 10 to the minus 6, because that would not give you the correct answer here. And then to find P2 on its own, we can divide the left-hand side in your calculator by 1.10 times 10 to the minus 6, and putting that into your calculator should give you an answer of P2 equals 153 kilopascals, where we're using kilopascals again because P1 was also in kilopascals. And that gives us the answer D here. Question 18 says the size of the buoyancy force Fb acting on an object immersed in a fluid is given by the relationship Fb equals rho GV, where rho is the density of the fluid in kilograms per cubic meter, g is the gravitational field strength in newtons per kilogram, and v is the volume of the object in cubic meters. The volume of an object that experiences a buoyancy force of 360 newtons when immersed in a fluid of density 1020 kilograms per cubic meter is. Well, notice how this is an unseen formula, so what we need to do is just plug the numbers we're given into the equation and rearrange for the volume in this case. And this is just testing your skills. So writing down our equation, we have Fb equals rho GV. Substituting in the numbers, we have 360 newtons for the force is equal to 1020 for the density times 9.8, which is the gravitational field strength on Earth, times v for the volume, which is what we're trying to find. Then to find v on its own, what you can do is take the left hand side, 360, and divide it by 1020 times 9.8 in your calculator to get an answer for v of 0.036 cubic meters. And that means our answer here is A. Question 19 says the diagram represents a wave travelling from x to y. So here's our wave travelling from x to y, and we're told this full length here is 24 metres between x and y. It says the speed of the wave is 48 metres per second. The frequency of the wave is. Well, if we're asked to calculate frequency and we're given a speed, then chances are we're going to use the wave equation v equals f lambda. So to find the frequency, we need the speed which we're given and the wavelength, which we can get from the diagram. So because we know the full length from x to y is 24 metres, and if we count the number of waves shown here, we have all the way up, all the way down and back to the start, that's one wave, all the way up, all the way down and back to the start, that's two waves, and lastly another full wave there gives us 3 full waves in total. So if we want to find the distance from the start to the end of one wave, i.e. the wavelength, then we need to take the full length 24 metres and divide it by 3 waves. So doing that gives us lambda equals 24 over 3, which is 8 metres. And then we can use the equation v equals f lambda to find the frequency. And then rearranging for frequency f, we can divide both sides by lambda to get f equals v over lambda, and then substituting in the numbers gives 48 divided by 8. And doing that in your head or putting that into your calculator should give you an answer of 6.0 Hz, which is the answer C. Question 20 says the letters X, Y and Z represent missing words or phrases from the following passage. Infrared has a X wavelength in visible light, infrared diffracts Y than visible light, and the speed of infrared is Z visible light. Which row in the table shows the missing words or phrases? Well, I'm just going to quickly list the order of the members of the EM spectrum down the side here. So we have radio, TV, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. And remember at radio waves that's a high wavelength or low frequency, whereas at gamma rays it's low wavelength or high frequency. So for the first sentence there, infrared has a something wavelength in visible light. You can see that if this is increasing wavelength towards the top, then infrared has a longer wavelength than visible light. So that means X must be longer, so our answer is going to be A, C or E. We then have infrared diffract something than visible light. Well, if infrared has a longer wavelength than visible light, then remember longer wavelengths diffract more than shorter wavelengths. So that means Y must be the word more, so we're looking at either C or E as our answer. And lastly, the speed of infrared is something visible light. Well, remember infrared and visible light are both members of the electromagnetic spectrum, so they must travel at the same speed, which is the speed of light. So that means that Z must be the same as. So to summarise, for X, Y and Z, we've got longer, more and the same as, which gives us the option C here. Question 21 says the diagram shows the path of a ray of red light as it passes through and out of a semicircular glass block. So you can see the ray of light going from glass back to air there, and it says which row in the table shows the angle of incidence in the glass and the angle of refraction in air. Well, here we just need to remember our definitions of angle of incidence and angle of refraction. And notice how this is our instant ray since it's the first ray, and then we have the refracted ray. And remember, angle of incidence is defined as the angle measured between the normal and the instant ray. So there's our normal, there's our instant ray, so it must be this angle in here. So that means to find the angle of incidence, which we could call little I, is equal to 90 minus 70, because this creates a right angle, remember, which is equal to 20 degrees. And then to find the angle of refraction, remember that's defined as the angle measured between the normal and the refracted ray. So that's going to be this angle in here. So this time to find little r, the angle of refraction, we can do r equals 90 minus 58 to get 32 degrees. So that means we have 20 degrees for the angle of incidence and 32 degrees for the angle of refraction, which gives us the answer A here. Question 22 says which of the following statements describes the term ionisation? Well, remember ionisation is the addition or removal of an electron from a neutral atom to create an ion, i.e. a charged particle. So the one closest to that definition is B, the removal of an electron from an atom to form a charged particle. Question 23 says, in a radioactive source, 1.8 times 10 to the 6 nuclei decay in 10 hours. The activity of the source is. Well, because we've got the number of decays in a time here, we're going to use our activity equation, A equals N over T. Substituting in the numbers gives 1.8 times 10 to the 6 divided by 10, but notice how we've got hours and we want that in seconds. So to get from hours into seconds, we need to times by 60 twice. So we have 10 times 60 on the denominator there, and putting that into your calculator should give you an answer of 50 becquerels, which is the answer E. Question 24 says a sample of tissue receives an absorbed dose of 0.20 micrograys from a source of alpha radiation and an absorbed dose of 6.0 micrograys from a source of slow neutrons. The total equivalent dose received by the sample of tissue is. Well, to find the total equivalent dose here, because we've got two different types of radiation, we need to use two equivalent dose calculations. So starting with the alpha radiation first, we can use our equation for equivalent dose in terms of absorbed dose and radiation weighting factor. So that's H equals dWr, and then substituting in our numbers, we have 0.20 for the absorbed dose times 20, which is the radiation weighting factor for alpha particles from the datasheet. And putting that into your calculator or doing it in your head should give you an answer of 4.0 microsieverts. Now notice how our final answer is in microsieverts, so that's why I didn't convert that prefix of micro there into 0.20 times 10 to the minus 6 grays. It's because I know that my final answer is in micro, so as long as I remember that this is still in micro, then my final answer here must be micro. And now we can do a similar thing for the slow neutrons, so we have H equals dWr, which is equal to 6.0 times 3, where 3 is the radiation weighting factor for slow neutrons from the datasheet, and that gives you an answer of 18 microsieverts. And then to find the total equivalent dose, we simply just need to add these together, so we have 4.0 plus 18 is equal to 22 microsieverts, which is the answer C. Lastly, question 25 says a technician carries out an experiment using the apparatus shown to determine the half-life of a radioactive source. We've then got a clock and then a Geiger-Müller tube connected to a rate meter, a radioactive source and a stop clock. It then says before carrying out the experiment, the technician measures the background count rate. The technician takes readings of the count rate displayed on the rate meter every 60 seconds for a period of 20 minutes. A graph of the technician's measurements is as shown. So we've got corrected count rate in counts per second on the y-axis and time in minutes on the x-axis. And you can see we get this gradually decaying curve there. It then says which of the following changes would allow the technician to more easily determine the half-life of the radioactive source. So we've got take readings of the count rate every 30 seconds for 20 minutes, take readings of the count rate every 60 seconds for 40 minutes, place lead shielding around the radioactive source, move the radioactive source closer to the Geiger-Müller tube, or move the radioactive source further away from the Geiger-Müller tube. Well, what we can say here is that to determine the half-life of the source from the graph, we need the curve to fall below 200 counts per second, since the initial activity was 400 counts per second. So there's the graph, there's the initial activity at 400 counts per second, and remember to find the half-life from a graph, we would need to halve the starting activity, which would be 200, and then go along to the curve and down, and that would give us our time, which is the half-life. However, you can see initially that it's not going below 200. So how do we get that below 200 counts per second? Well, we would need to time for longer because we've only timed for 20 minutes there. And you might be wondering why it's not the first statement, take readings of the count rate every 30 seconds for 20 minutes. Well, what you would be doing there is adding more points onto the graph here on this line, but it would still form the same line. You still get the same relationship going down to this point here after 20 minutes because you're only timing for that length of 20 minutes. Whereas if you had a curve that came gradually further down over 40 minutes, then you would be able to determine the half-life from the graph. So that means our answer here is B, take readings of the count rate every 60 seconds for 40 minutes. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.